Right, so now we have an idea of how dynamic programming works and why it's okay to write down things like value functions. We can start to move forward with a few applications. Now the first thing we're going to do is to look at something we actually haven't looked at so far. So far we looked at the basic growth model and we observed that we can apply dynamic programming methods to it. But something that's missing from it that you would think we should be looking at if we're in an economics class is markets. So far we looked at the behavior of one person, or again it could be a continuum of people who are identical. Where are the markets for the consumption good or the investment good? Where are the markets for the resources, capital, and if we extend it to allow for labor, labor? What we're going to do now is have a look at a version of the growth model where there are markets, and then we're going to realize that the solution to the market problem is actually the same as the solution to this other problem where we were just sort of maximizing things as though we were finding the best possible outcome. This is going to lead us to discover the first and second welfare theorems of economics. The first welfare theorem says that unless there are externalities or other market failures, the market outcome is going to be Pareto efficient. That means that it's impossible to change any allocation of resources or commodities more generally without making someone worse off. In a context like this where everyone's identical, it means that it's the best possible outcome for everyone. The second welfare theorem is sort of like the reverse. It means that for any Pareto optimal outcome, it's possible to find a set of prices for all the commodities and resources and a distribution of whatever endowments there are in this economy, whatever agents start with, such that that Pareto optimal outcome can be supported as an equilibrium in a market setting. So let's go and look at that now. In this model, on the demand side, we will have households. And we can think of a household as having only one person in them, or many, as long as they share utility over their joint consumption, it doesn't really matter. That's going to be useful later when we try to introduce population growth. For now, let's abstract from it and say that there is a fixed population that we call households. Now, the households have a utility function as before that includes the sum of discounted consumption, or rather the sum of the discounted utility from consumption at dates t to infinity. And this is what they maximize. And they maximize it subject to, well, the broad type of constraint here is going to be subject to the constraint that their expenditures may not exceed their income. Now, what's income for these households? In this model, we're going to have that households may work. We're going to call the time they spend working labor and refer to it as N. And for each unit of N that they spend working, they get a wage W. Now, notice that I did not put N as being in the utility function. Later on, we will include it because, of course, time that you spend not working is time that you can use to enjoy leisure. So leisure, the time left over after you finished working, could be in the utility function. It's not there. And so And in fact, these people will spend all of their time working. We're going to have that the agents are endowed with 1 unit of labor every period. So of course, this means that they will set n equals to 1, since there's no leisure here. So one source of income is work. Another source of income is going to be that these households are also the ultimate owners of the capital in this world, which is going to be a productive resource, just as we've seen before. And we're going to say that capital is rented out and earns some rental rate R at each period, RT that is. So this is going to be their income. I suppose, in principle, if there were any profits to be earned from firms owning any companies, those would be added in here. As we'll see in this environment, at least for now, there will be no profits. So this is their income, and that must exceed their expenditures. Now, there are 2 things that they may spend on. One is consumption, and let's say that consumption has some price. And the second is investment, which could also have a price. Now, what we're going to see is that because investment and consumption are both uses of the same final good, the price of these 2 things is equal. And we will have an additional possibility, which is that we can set one of these prices, P, W, or R, to equal 1 if we wish at each date. That's calling one of these things a numeraire, which means it's the good which you decide to use as a unit of account. So let's just get rid of this, because we're going to use the final good here, which can be used for consumption or investment, as the unit of account. Great. The households will also keep into account the fact that their capital tomorrow is going to equals whatever is left of their capital today, the undepreciated portion of their capital, plus investment. So that's what investment is for. The supply side, the production side of this economy, is going to be a continuum of competitive firms, and they will produce output according to some production function of both capital and labor. And I'm just going to go with the following, just for simplicity. This is what's known as a Cobb-Douglas production function. The key feature of it is that this features constant returns to scale. In other words, if you multiply, what constant returns to scale means is that if you multiply the amount of capital by some factor, and you multiply the amount of labor by some factor, what you get is that you end up multiplying output by that factor as well. And you can easily see that this is such an example. If I multiply K and N by some fixed factor x, you're going to get this output. So this satisfies constant returns to scale. And the firm also will have its own separate maximization problem. So the firm here is autonomous. It's not operated actively by the households. What it does is that it maximizes its profits. What are its profits? I guess using the notation from before. Its profits are that. And what it does is that it's trying to maximize, well, profits, of course, the revenues minus costs. The revenues are this. I'm going to drop this because we said that the final goods price is 1. And of course, let's replace this with that. And their costs are, of course, that they're going to have to pay wages for any labor that they use. They'll have to pay the interest rate for whatever capital that they use. So what they're choosing are K and N. And this is a static problem because there's nothing in the firm's problem that means that it needs to take into account any future factors constraining its behavior or that might affect its optimal behavior today. So we can just focus for now on the static profit maximization problem. Now let's next go to the solution. In the solution to this model, the household's problem can be simplified because we know that because of local non-satiation of the utility function, this is going to hold with equality. And that means that we can simplify a bunch of stuff here and say that what they're maximizing is this. And then we have this constraint that holds with equality. So we can use that to replace investment here. And that makes life simpler. Moreover, since we know that n is between 0 and 1, they don't care about leisure. In this example, we know that n is going to equals 1. So we have an even simpler problem. And now, of course, we can make this very simple by writing it down as a dynamic programming problem, where we have V of K is equal to the max, KT, I guess, of this plus the discounted value of V that takes KT plus 1 as its argument. There. Now we introduce the first order conditions, which are straightforward. First order condition of this thing with respect to capital is just going to be, well, with respect to KT plus 1 is going to be this times minus 1, which is the derivative of what's inside here with respect to capital. That's the chain rule. Equals b prime. Sorry, plus v prime equals 0. Of course, that can be rearranged like so. The next thing we need is the envelope condition. And for that, we need to derive this with respect to k. And we get k prime equals u prime times the derivative of what's in here with respect to kt. Now, the derivative of this with respect to kt is nothing. The derivative of rk with respect to k is r. This doesn't show up. And the derivative of 1 minus delta k with respect to k is k. So, here you go. The Euler condition is the marginal utility tomorrow times the interest rates and taking account of depreciation. Now, finally, the Euler equation requires that we put these two conditions together. And so we'll get this. We have to replace this here. And we have to then be careful that anything that's t before is now t plus 1. And you'll see that this means that the household's problem is solved by a difference equation, a second order difference equation, because it has kt plus 1, and over here it has kt plus 2. So there are going to be infinitely many solutions to this, but there will only be one that satisfies the transversality condition, and so that's the one we'll look at. Great. Now, this was looking at the households. Now let's look at the firm. Firm's problem is very easy. By comparison, it's static. So we just need here that the derivative of this with respect to k has to equal the interest rates. And the other first order condition will be that the derivative of this with respect to n should equal the wage. That means that, of course, all the resources here get their marginal returns. An implication of this, mind you, is that because this production function satisfies constant returns to scale, these conditions mean that, in fact, we will have zero profits in this environment. To see that, let's go to sort of a footnote. Here is what we have. We have output, and we had these two results. Now we know that y is constant returns to scale, which tells us that if you multiply capital by x and labor by x, then you end up with x times the output. Now let's divide both sides by x. We get this. And now let's send x to 0. So in the limit as x goes to 0, what are we going to end up with? Well, L'Hopital's rule tells us that we should derive the top and bottom of this by x. And so the derivative of this by x is just 1. So it's gone. And the derivative of this by x is, of course, this plus that times k times n. So where does that get us? Remember that the profits here are YT minus WN minus RK. And this is telling us that R is this. And it's telling us that the wage is that. And of course, that means that the profits are equal to YT minus YT, which is 0. So with constant returns to scale, we will have 0 profits. That's useful because it means that we don't need to worry about how many firms there are, who owns them, and things like that. You can just solve the firm's problem, and we end up with these rules regardless of whether there are 2 firms, 10 firms, 1,000,000 firms, or continuous firms, or anything like that. We don't need to worry about it. Thus, we will refer to this as an aggregate production function. It's as though there were just one giant production function. Everyone owns shares with it. It hires labor and capital, rents capital, produces output, but there are no profits because everything, all the returns are distributed to the resources, to the owners of the capital or to the owners of the labor. Now, putting this all together, this means that the equilibrium of this environment is going to be described by the transversality condition and by this. The rental rate of capital is going to be that. The rental rate of capital tomorrow is going to be that. Actually, in a way, I'm overdoing this because, of course, we know what n is going to be in this environment. We know n is going to be 1, but let me just finish this because it's going to apply in the more general case where agents might actually care about leisure. Is that done? Almost. There. And so this is the Euler condition that's going to describe the evolution of this economy along with transversality. Now let's keep that there for a moment. And now let's look at what this problem looks like if there were no markets. We're going to call this the planner's problem. And it assumes that there is some entity that we call a social planner that does the following. It's going to try and solve the household's problem without any markets. It's just going to be subject to the constraint that this, what the households can get, the consumption investment, cannot exceed the total amount of resources that can be spent are the output itself. Now, of course, this planner has these constraints to worry about as well. So what we're going to do is we're going to proceed as before and just plug these constraints in here. So then this is output minus investment. And then again, we can use this constraint in order to replace this with investment and the undepreciated capital. And again, if we want, we can replace n with 1 because we know it's 1. So now we take this thing, and again, as before, we could give it a recursive representation. We should not call it the same thing as V, because it isn't. Let's call it V squiggle with capital, V tilde, okay. For those of you who like things to be correct. Of this plus V tilde tomorrow. There. And what are we going to get? Well, now we have to take first order conditions again. And what are we going to do? The first thing we have to take with respect to, well, okay. Let's forget labor, sorry, we know it's going to be 1. You could plug it in everywhere. And as a result, the only thing that they're deciding is about their capital tomorrow. And so what we're going to get is that the derivative of this with respect to capital tomorrow times the derivative of what's inside the function u, which is minus 1, must equal the derivative of v squiggle. And then there will also be an envelope condition, which is that the derivative of this with respect to capital has to equal the derivative of this times the derivative of that with respect to k, which of course is, if you look carefully, let's just paste the whole thing in so that we're not rushing. The derivative of this first part with respect to k is just f sub k. The derivative of this part with respect to k is 0. The derivative of this part with respect to k is 1 minus delta. And the derivative of this with respect to k is 0. We put it all together, and we end up with an equation where, again, we have to go through here carefully to make sure that the dates are correct, because we are putting in not k as we were in the Euler in the envelope condition, that k in the future. Now finally, let's compare this Euler equation to this one. I'm going to copy it underneath. I'm going to have to clean it up a little bit. I'm going to contend that these two are exactly the same. How come? Well, the reason is straightforward. First of all, notice that this is actually originally this condition. The reason we don't have n there is because we plugged in 1. And you remember that because f is constant returns to scale, this actually equals output. So we can replace this with output, right? Oops, sorry, that's going to be the minus there. Or there. Kudos to those who noticed. Now, what else can I replace here? Well, here is the same thing. This is also output tomorrow, except that it's at date t plus 1. So let's give it a plus 1, plus 1. And there you have it. The two are actually the exact same condition. So the Euler equation that you get from the market problem is the same as the Euler equation that you get from the planner's problem. How come? Well, it's pretty straightforward. The planner is going to choose input use so that it ensures that the marginal return from it is optimal. This household is looking at wages and interest rates, but those are set by the firm to make sure that the resources obtain their marginal return. So at the end of the day, of course, the market solution up here and the planner's solution down here end up being the same. And so this is an example of the first welfare theorem, where we have that a market equilibrium allocations are Pareto optimal. There's nothing you can do here to make anyone better off. They're all identical, of course. And so in this context, it means that the markets, this is a way of saying that markets are efficiently using resources. There is nothing you can change here that would make anyone better off.